Okay, so today we're going to go through this conservation of energy worksheet. The worksheet is right here. It starts top. Pull in my camera. You guys will need to pull out a piece of paper or however you're going to record this information, because this is what you're going to turn in today, is just what we put on the recording. So today we're talking about conservation of energy, but we're also talking about that transfer of energy between kinetic and potential. So conservation of energy. I want you to think for a little bit about the skate park simulation that we did. When think about that graph. At the very top of the hill, it was all potential energy. But then as it went down, kinetic increased and potential decreased. And that's what we're going to show with math today. So if we look at our worksheet here, we can see, let's get a little bit. If we look at our worksheet here today, we can see there's a formula that we're going to be looking at, we're going to be using. And then there are also the old formulas that we had. The potential energy is mass times gravity times height. Kinetic energy is 1/2 mass times velocity squared. And we'll continue to use 10 for our gravity just to make it consistent. So let's go ahead and write that formula, the new formula, down into our notebook so that we have it, so that we can use it on tests and quizzes and everything. So potential energy before plus kinetic energy before equals, and I won't write them all out for space, potential energy after plus kinetic energy after. Now, there could be a whole lot of math going into this, because sometimes we're going to have to plug in the formulas that we have used before. All right, so you want to be really mindful of that. Some of these word problems are going to take a little bit of real thinking to get through. Also, remember when we had potential energy, mass and gravity are sometimes put together to get newtons. So sometimes we can just use newtons times height. And we'll talk about that as we go along. But let's jump into the problems and we'll look. Let's look at the picture. 100-kilogram roller coaster, and I know it's labeled number 3. It's really okay. We'll just ignore that it says number 3. 100-kilogram roller coaster comes over the first hill at 2 meters per second. So right here, we're going 2 meters per second. All right. The height of the first hill is 20 meters. All right. So h is 20 meters. So this is also h at point A. And then h divided by 2 is point B. And then c is all the way to the ground. All right. It says find the total energy for the roller coaster at the initial point. Okay. So what we're going to think about is, what does a point mean? The starting point, and just a very tiny spot in time. We are going to assume that at that point, you're sitting still momentarily at the top of the hill. Okay? So when we assume that, we are, I'll just put 3 total energy. When we assume that we are sitting still at that point, then we can use the potential energy formula. Mass times gravity times height. So the mass of my roller coaster is 100 kilograms. Or my roller coaster cart, I guess. And then the gravity is going to be 10, because that just makes it easier for us to use 10. And our height at that point was 20 meters. So then 100 times 10 is 1,000. Times 20 is 20,000. And our unit would be kilogram meters squared, because meters times meters, over second squared, or joules. Okay, so that's the first part. It said, find the total energy. Okay, that's our first total energy. So then it says find the potential energy at point A using the PE formula. Huh? That is exactly what we just did. What you got? Oh, the unit? The unit is kilogram meters squared per second squared, or joules. Remember how we talked about joules are the unit of energy? Okay. So just like he just said, number 2 is asking for potential energy. We already did potential energy. So this is actually 1 and 2. I won't make you do it twice, because we use that formula to find 20,000. And when we look at the formula, remember what we said, at point A, we're assuming at that moment in time, we're sitting still, so we have 0 kinetic energy. Right? And we kind of think about that skateboarder simulation that we did the other day too. All right, let's look at the next question. So we did 2. Number 3 says, all right, now we're going to use this conservation of energy. Use the conservation of energy to find the kinetic energy at point B. Okay, that's critical in what we're looking at, because let's go ahead and lay out our problem. If we know that potential energy before plus kinetic energy before equals potential energy after plus kinetic energy after, we are looking for kinetic energy. All right. So we know that at point A, our potential energy is 20,000 joules. Right? That is our B4, because we said we figured the potential energy. We said we were sitting still at the very top point, so we had 0 kinetic energy. So we're going to take this number right here and put it in there, because that was our starting energy. That was our before energy. That's what we figured out. So we can say equals, right now, potential energy at point B, we're going to have to figure again. So mass times gravity times height. Let's look at point B again. Point B has 1/2 the height. So we have the same roller coaster car, 100 kilograms. We're on the same planet. Okay. Now, what is half of the height? We had 20 meters before. 10. Right. And we don't know KE. That's what we're trying to find. And we figure out what we can figure out.
I have a question. What's the formula for whenever you have the mass and then you square the
velocity? It's the kinetic energy formula. Because,
just use that.
Well, you could, except that you don't have a velocity given at point B. So, like that's a great question. He asked if you could just use the kinetic energy formula. Well, you're given a velocity at the first hill, but you're not given a velocity at point B. So that's why you got to figure it out. And I mean, that's a good thought, but we're not given that velocity. And you know how you go on a roller coaster and sometimes you go faster than you go at the beginning. So, all right, let's go ahead and finish that part, and then we'll go on to the other questions. So 100 times 10 is 1,000, times 10 is 10,000. Okay, so all right, so we're adding here in this formula. If we have to do the opposite math to get rid of it, what do I need to do? I need to subtract my 10,000. So that's where those algebra skills that you learned before come into play. So I'm going to subtract 10,000 and gives me 10,000. Because algebraically, if I am adding it right here, I have to do the opposite math operation to get rid of it, like when you have a single step, in algebra. And that's what we have. We don't know this variable, so we're going to subtract it so that 0 plus this is just it by itself. And then we subtract on this. We have to do the same thing on both sides. And then we get that. So this is our kinetic energy at point B. So we'll label it and make it clear. Okay. Let's look at the next one. Find the potential energy at point C. If we go back to the picture, it says potential energy. So at point C,
Well, we haven't solved the tree.
didn't it? 3 says use the conservation of energy to find the kinetic energy. So that is the kinetic energy at point B. Is that 10,000?
So I was right to just use the kinetic energy formula.
But you didn't have a velocity that you could use. And the problem says use the conservation of energy formula. So I'm just showing you the way to do it with the problem that you're given. So if you got the right answer, that's good. Potential energy is mass times gravity times height. And it says that we're supposed to find the potential energy at point C. Right, here's point C. Point C is all the way on the ground. So its height is 0. We have the same car. We have the same planet, so we're going to have the same gravity. But our height is 0 because we're on the ground. I mean, you could argue that a roller coaster doesn't really go flat on the ground. You could say that, but for our purposes, the diagram puts it right at 0. So 0 times anything is 0. So the potential energy, thank you, at point C is 0 kilogram meter squared per second squared. Okay, because C is right on the ground. Yes, sir. You can just put joules for that. I want you to make sure and realize that when you say joules, you're really saying kilogram meter squared per second squared. Because canceling out those units is going to come into play as we get into some other of the modules that we're going to. All right. All right, let's look at 5 and 6, and then we're done. So this one, again, it says to use that conservation of energy to find the kinetic energy of the roller coaster. Scroll over. Of the roller coaster at point C. So we're working at point C right now. So since it tells us to use that one, we're just going to use that one for the practice of it. right, so we calculated earlier that the original energy that we had was 20,000 joules. So we're going to start with that again. And then we just figured out that at point C, the potential energy is 0. So and it's telling us to find the kinetic energy. So 0 plus anything is itself. So we're left with Ke, when kind of made it easy on us, equals 20,000 joules. Because we had to calculate that potential energy, put it into the equation. Okay. And then I'm just going to slide my notebook over for number 6 so that we can go back to what we already did and look at it. But number 6 tells us Number 6 tells us to use the kinetic energy from C to find the velocity of the roller coaster at that point. So we know that we're going to use the kinetic energy formula, 1/2 mass times velocity squared. If we look back at 5, we had earlier is 20,000 joules. So our Ke is 20,000 joules. We have the same roller coaster car because nobody got off the roller coaster. And we don't know the velocity. All right. So what can we figure out? Well, we have 20,000 joules. 1/2 of 100 is 50. And we still don't know velocity squared. So again, with that same algebraic thinking, if I'm multiplying here, I have to do the opposite math problem, the math operation, in order to get rid of it. So I'm going to divide by 50 kilograms. And that gives me b squared on this side, but then 400. Now here's where understanding that unit really comes into play. Because if I divide by kilograms, I'm left with meters squared over seconds squared. Now, have I found the velocity yet? No. I still have to take the square root. So then if I take the square root, I have v equals, and I did this one earlier, so it's not that I can do that in my head. I already put it in a calculator. The square root of 400 is 20 meters per second. So when we have them squared here, they turn into meters per second, which is a unit of velocity. 20 meters per second.